I wanted to thank the team at Gurobi for letting me share a little bit of how we use optimization at East Daley. This is something I have really enjoyed working on, and it's something I enjoy sharing with people. So I'll start by talking a little bit about East Daley. We're a small business in Centennial, Colorado, and we're trying to reshape the way that markets use data to quantify risk in the North American energy infrastructure, midstream, and E&P companies. One of the things that makes us the most unique is the fact that our analysis considers both commodity and financial dynamics. So there's a lot of research available that might just be commodity research or just financial research. But you start to learn a lot of really valuable insights when you put those two things together. So maybe from a commodity perspective, you're looking at supply and demand at a macro level, and the price of oil might go up or go down, and so you'll come out with some commodity analysis that says, hey, everyone's going to stop producing oil because, or slow down producing oil because of price dynamics. But when you start to pull the financial information in, what you might realize as well, some of these companies have debt obligations, they have contracts, they have different things that may not permit them to do what just the pure commodity analysis would suggest. As well as, so let's say you have a handful of companies that continue to produce more or grow, that also is going to then re-impact the commodity side of things. So by putting those two things together and having that kind of that tension, we're able to see a lot of things that you wouldn't necessarily get to see if you just considered just the commodity or just the financial aspect of the situation. So like I said, we primarily look at the midstream. So here's a simplified diagram of the midstream, and this only is gas. There's a whole nother kind of supply chain related to oil that we're not going to cover today. But so on the very far left, on top of exploration and production, you have wells and rigs. So a rig will show up, it'll drill a hole in the ground, and you hope to get some sort of hydrocarbon out of it so you can start making lots of money. From the well, there's gathering systems. We have wet gas gathering that's going to go to a cryogenic gas processing plant, and that's where they are going to extract the NGLs out of the gas. So the NGLs will continue on in an NGL pipe. The residue gas will then go be injected back into the natural gas transportation system. From the NGL pipeline, you go to a fractionator where the NGLs are further broken up into the specific individual purity products. From there, it goes to storage or transported to an end user. Down on the bottom again, you have the natural gas. It goes transportation systems, long haul pipelines to storage, and then to end users, power plants, heat, industry, different things like that. So we try and quantify risk in this system. So let me ask a few questions. If the price of oil goes to $30, what's going to happen? So like I said, there's lots of commodity research out there. And so people can look at trends and say, $30, this is what supply and demand looks like, this is what historically has happened, and people might come up with a, hey, this is going to be the total, say national or maybe global oil output at $30. But what's going to happen to this individual fractionator? And at this point, it's important to note, I said this is only gas, and I'm talking about the price of oil, so there's kind of a disconnect there. But it's important to know that in the majority of cases, North American natural gas infrastructure is primarily driven by what's happening with oil. In most places of the country, gas is actually a byproduct that you have to deal with, not what they were actually primarily targeting. So price of oil goes to $30, oil production is going to change. That's going to change the amount of gas that goes through the pipelines. And at a macro level, you might be able to answer that question. But at a micro level, with a specific company or a specific fractionator or a specific pipeline, it becomes a little bit more difficult to answer at a high level, and you need to start to understand the individual assets. What if there's a hurricane in South Texas? Now we're not quite so global, we're very regional, and so there's only going to be a certain subset of assets that are affected. and you can't use the same high-level analysis. If a specific company is at risk of bankruptcy, what will happen? So do all the pipelines face the same risk if a company's at risk of bankruptcy, or is it specific pipelines? And at that point, it becomes important to know, well, which pipelines, does that operator ship products on, and how are they connected to other assets? And then let's go really specific. If a drilling rig drills a well at exactly 31.7 degrees north latitude, negative 101.9 degrees west longitude, what will happen? Now all of a sudden we're very, very specific of, well, I need to know which gathering pipelines are there, which processing plants are there. That way I know which individual pipelines and eventually end users will be affected. So that's the supply chain. That's what we really try and do. We try and help people understand the risk at an asset level as opposed to just high level market dynamics. And this is a complex supply chain. So for the rest of this presentation, we're only going to focus on a specific portion of the supply chain, and that is the gathering and processing, which is connecting the wells to the gas processing plants via gathering pipelines. So I know not everyone today tuned in to just get an overview of how the midstream sector works. So optimization comes into play. So I just absolutely love this comic from XKCD. In the far left panel, you have this person. They've written some wonderful code. They took an impossible problem and they solved it. So up in the top right, we have academia, where they're so excited. They get papers, they get textbooks, various different things. And then down in the bottom right, you have the business owner that says, great, you fixed my problem, now can you fix the printer? And this is how, a lot of problem solving happens in business is, you're excited from an academic standpoint, but at the end of the day, what we're really here to do is just solve problems. However, historically, this wasn't possible. So if you go back, and by no means am I an expert on any of this, but and look at kind of the history of integer programming, when it first came out, people formulated integer programming problems and said, oh, we're going to go off and we're going to solve all these wonderful real world problems. But unfortunately, due to technology, both hardware and software constraints, most of those problems weren't actually solvable. And so businesses kind of, to some degree, gave up on using integer programming. So with that in mind, get back to gathering and processing. So we have our well, we have our gathering pipe, we have our processing plant, and they're connected. And this is a really simple supply chain, one well, one plant, right? Well, let's look at what this looks like in practice. So this is just a zoomed in portion of a few counties in Texas. And you can see that there's just this massive network of pipelines. There's just tons, and I'll even say this map is incomplete. There's a lot of pipelines that aren't even on this map. There's hundreds of processing plants. So each one of these little triangles represents a different cryogenic gas processing plant. They each have different capacities ranging from, 10,000 cubic foot of gas per day to hundreds of thousands of cubic feet of gas per day that they can process. And what we do is we like to group them into systems. So, you might see a couple plants that are very close together. Oftentimes those plants are owned by the same company and interconnected. And so instead of thinking of each individual plant, what we're going to do is think of systems of plants and that have, similar characteristics. And there's millions of wells that I'm not even going to show on this map just because it makes it too cluttered and you can't see what's going on. Okay, so in a perfect world, we want to understand risk on this natural gas supply chain. So we want to understand exactly how it operates. So we know that there's two processing systems, A and B. We might know the throughputs of those systems. So it'd be nice to know what the throughput looks like on each system, because the throughput's directly related to what they can feed into the connected NGL pipelines and the residue gas. And would love to know which wells are feeding those systems. So if I know that wells 2, 4, 5, 6, and 7, and 3 are feeding processing plant A, when I forecast the volumes for those individual wells, I then know what the forecast looks like for the plant, and then I can forecast pipelines and just propagate all those changes throughout the supply chain. Similarly with B. So in a perfect world, I want to know everything about the supply chain and how it operates. But in reality, the data is not perfect. So because we're selling and helping financial institutions understand risk, we have to use publicly available data. So we collect this from state and federal regulatory agencies, and we don't have any proprietary data that comes from the companies themselves. So because it's regulatory data, it's not perfect. There's gaps. So for the processing system A, we may know that, hey, there's a certain period of time that we don't have throughput. Same with B. We also don't know which wells feed which processing systems. So there's data sets available on processing plants. There's data sets available on wells, but there's actually no data set that says these two are connected. We know that they're physically connected because the gas has to be transported via pipeline, but there's really no data that actually says which wells are feeding which processing systems. That's not proprietary and owned by these specific companies. In rare cases, let's say there's a bankruptcy filing or a well is purchased, you might find in the purchase agreement some information saying which processing system it feeds, but by and large, most wells you don't know this for. And so looking at this picture, now we can't answer those questions we had originally hoped to. If you wanted to know if well number 3 goes, or well number 12 goes down, and you want to know which processing system's affected and which NGL pipeline system's affected, unless these things are connected, you can't answer those questions. So remember the goal, we wanted to answer those detailed questions about the supply chain. So we need to systematically come up with a model that connects each well to a processing system. That way we can have at least a modeled idea of all the drivers going throughout this supply chain. So before I walk through the model, I'm going to add a disclaimer that this is personally how I like to build a model. It's not necessarily a discussion on modeling best practices. I'm sure there's numerous ways that each one of these constraints could be written, different ways you could represent the problem. By no means do I say this is the best way to do it. I also know that there's tons of resources available. I know Gurobi has a lot on their website that talk a lot about modeling and different implementation topics. So there's a lot of other resources you can look at if you're specifically looking at modeling best practices. But this is how we have built the model at East Daley, and it seems to work well for us. So what are the things we can decide? What are the choices we can make? So we can determine which wells provide input volumes to which GMP systems. We want to align that with any known facts. So, back to the incomplete data, we don't have perfect throughput data for each processing plant, but we do know specific cases of, hey, in this time period, the throughput was, we'll say 100,000 MCF. Okay, well, if we know that in this time period, the throughput was 100,000 MCF, then let's make sure that the wells we have feeding that system also produced 100,000 MCF during that time period. So volumes is a large part of those facts. Another set of facts we might have is geography. So if we have a well that's in Texas, it's likely feeding a processing plant in Texas or maybe a nearby state like New Mexico. And then lastly, given multiple choices, choose the best one. So this speaks a little bit to quality of, hey, when we're determining which wells feed which GMP systems, we want to make good choices. Now, I'll wait a little bit before I define what is a good choice, but just know that that's what we want to do. Okay, so we're going to determine the wells that provide the input volumes. So those are our decision variables. And we need to make some assumptions. So the first assumption we're going to make is that every well can only feed one processing system and 100% of the volumes go there. So if you have a well that produces 10 MCF, it doesn't send 5 to a processing system and just not send the other 5. It also doesn't send 5 to one processing system and 5 to another. It's 100% dedicated to a single system. This isn't always 100% true, but this is by and large true just because of the cost of connecting a well to multiple systems. And so it's a assumption we're going to make. We're also going to assume that it's constant within the time period in question. So if we're looking at 36 months, we're going to assume that every well stays dedicated to a system within that 36-month window, and they don't switch from month to month. So let's add in some data. We're going to need a set of wells. We're going to need a set of systems. And we're going to add some binary decision variables that say xij is 1 if well I is allocated to system j, 0 if not. So how many variables does that create? The number of wells times the number of systems. So that's could potentially be a large number of binary variables if there's a large number of wells. And we're going to add a logical constraint that just makes the variable behave according to our assumptions stated above. So this is saying that summing across all the systems, one well can only be at most allocated to one system. We could make this an equality constraint, but making it an inequality actually helps the model find feasible solutions faster. And at the end of the day, if a well is not allocated to any system, we can allocate it to a balanced system in post-processing. Constraints. So we know we want to align with known facts. So we're going to add some more data. We're going to have a set of time periods. We're going to have a set of well volumes. So this is for each time period, how much volume of gas did every single well produce? A set of system volumes. So for each of those time periods, how much volume was the throughput on the system? And we're going to add a constraint that says the sum of the well volumes for all the wells allocated to that system equals the system volume at that given time period. Number of systems times the number of time period constraints. And then we also said facts for geography. So this is a map of the lower 48, all the oil and gas wells that have produced in the last 15 years. All the green dots represent an old or traditional vertical style well. All the blue dots represent a new horizontal style well. And you can see that, they're geographically distinct. So up in North Dakota, you have a bunch of new horizontal wells, and, down here in the northern corner of New Mexico, you have a bunch of old wells. Well, it's reasonable to say that no well in North Dakota is going to a processing plant in New Mexico. So we could add some constraints that would say that, but we also can just split the problem into multiple different problems. So instead of trying to do one giant problem to do everything, we can take these different kind of subsets of the data and say that they're distinct and split them into separate individual problems. So that's the first way that we're going to handle geography. Okay, so now let's get back to this idea of the best one. So with as many wells as there are, if we just had the volumetric constraints, you'd end up with lots and lots and lots of multiple optimal solutions where there's lots of similar wells that you could trade them in and out, and they would produce the same volume. But there's other characteristics that lead us to help rank whether a solution's good or bad. We're going to define a set of well to system costs. Those costs are determined through a number, a large number of different models that we're not going to get into today, but we look at specific distances. So each specific well, how far is it from each specific processing system? Who operates those wells? Is it a company that has a business relationship with the company that operates the processing plant? We look at what type of hydrocarbon is produced. Is it wet gas? Is it dry gas? Is it a high pressure system, a low pressure system? So we distill a bunch of different industry knowledge and we calculate these costs of what do we think it would take to allocate this well to this system. So not only do we want to line up the volumes, but we then want to line up the volumes in such a way that we get the lowest cost solution. And so at the end of the day, we just want to minimize those costs. So at this point, we do have a complete model. We have decision variables, we have constraints, and we have an objective function. But I can just tell you that it's not likely to be feasible or useful. And the reason for that is some infeasible constraints. So going back to this constraint that lines up the system volumes, remember we're working with imperfect data. And so this is going to be a problem. The fact that we said the well volumes need to exactly equal the system volumes is going to create a problem. If we have even a few wells missing, it's not going to exactly equal. Maybe the volumes were misreported at the system level or the well level. What can we do about this? Well, we can reformulate this as a soft constraint. So what we're going to do is we're going to add a set of variables f. These are not binary, these are continuous, which represents the units of constraint violation for system J in time period T. We're going to add some constraints to make that behave like we thought it would. So these two constraints are identical except for two things. So we're now saying that the sum of the well volumes allocated to that system minus the fit violation has to be less than or equal to the system volume. So what that's saying is if the well volumes is greater than the system volumes, you can subtract off some of that fit to get it back down into where it needs to be. And then we've measured what the constraint violation was from being over. The next constraint looks for the violation being under. So if the well volumes is not large enough, you add in some fit violation, and then you all of a sudden get to the exact system volume. It's important to note that except in the case where the well volumes exactly equals the system volumes, only one of these two constraints will ever be tight at any one point in time because you're either over or under. So F between the two constraints basically acts as the absolute value of the difference between the well volumes and the system volumes. And because we want to have as little constraint violation as possible, we're going to add into our objective function that we want to minimize the fit violation. So at this point, we talked about taking a constraint that wouldn't actually be feasible to imperfect data and making it a soft constraint. So I wanted to talk a little bit about linear constraints, and this somewhat lines up with what I was talking about earlier, where there was a large number of problems that got formulated as integer programs, and then we couldn't solve them. Well, you can model a lot of things with linear constraints. You can do if-then types of things. You can do either-or types of things. You can do max and min, and there's so many different things you can model with some different tricks, linear and integer programming. There's even a large number of things you can approximate. Using piecewise functions, you can look at squared error. So, where we were looking, the last slide, where we're looking at absolute error, we could actually approximate that as squared error by adding more and more constraints for different tolerances and thresholds. And then we can get an approximation of squared error. You can use different coefficients. Instead of doing absolute violation, you could do a percentage-based violation. So lots and lots of different things you can model with linear constraints. I do have to mention that there are still even a larger number of problems that are nonlinear that you can't solve using this technique, but a lot of things you can. So multiple objectives. So when working with soft constraints, important becomes an issue. So our original objective function, we wanted to minimize the cost. However, now we're minimizing the cost and the fit violation. Well, which one's more important? How heavily should they be weighted? Are they in the same units? That can start to really mess with how the objective function can operate. So there's two kind of main approaches for dealing with multiple objectives. First is weighting them. So we just literally say, okay, if cost is 5 times more important than fit, then we're going to multiply cost by 5 or divide fit by 5. There's also, you can use hierarchical approaches. So maybe we want to solve for the fit violation and then figure out what's the best fit violation we can get, and then within that solution optimize the costs. So you can do this yourself. If you want to do a hierarchical implementation, you solve the first model, you grab the objective function, you go throw that in, you add it as a constraint, and then you resolve with the new objective function. That potentially can lead to lots of bugs. It's a lot of extra work. And so I'm very thankful for the folks at Gurobi that their API has a very clean way of handling this, and you can literally prioritize, hey, I want to solve this objective first, this objective second. You can even do things like relaxation of, hey, solve this objective first, and then when you're solving for the second objective, you can relax the solution absolutely by this amount or relatively by this percentage. They also allow you to do weighted, so you can assign different scalars to each part of the objective function. And they even have a blended approach where you can kind of mix and match and use weights as well as a hierarchy. And this will save a lot of development time. It also saves, lots of errors and makes the code a little bit cleaner. So what does this actually look like? So here you can see from a code perspective, this is written in Python using the Gurobi Python API. The first part of the code is just loading the libraries. The second part is just populating data. So here, all the data is hard-coded, just as a demo to let this code run quickly. But it would be very easy to just replace each one of these data sets with a database call. So variables and constraints. So on line 42, we're just initializing an instance of the model. On line 46, we're adding the well variables, and you can literally just do a cross product of wells and systems. So I'm feeding in a list of wells, a list of systems, and it's creating a variable that's binary for every single well and system combination. Line 48 is adding in the constraints that basically say a single well can be allocated to at most one system. Once again, I really like the Python API. A large part of that is that, I'm used to writing things in a mathematical sense, for all, summing over, and they've brought a lot of that notation back in with the way some of the syntactic sugar that's available in Python. So the constraint reads very much like you would write it mathematically. Line 53, those are our continuous fit variables. It's the cross product of our systems list and our time periods list, and they're continuous variables. By the way, the naming is just, it's helpful when you're, debugging things. If you write an actual LP file, the variables will actually be named, F system 1, system, or time period 6. And then line 55 and 57 are adding in those constraints that are the fit constraints. So they should be identical, except the minus fit less than or equal to sys volumes, plus fit greater than or equal to sys volumes. So now to the objective function. So we wanted to minimize. So we're minimizing fit error and cost. So the first thing we're going to minimize is the fit objective. So this is how one of the ways you can define the multiple objectives. So we set our objective with index 0. So our first objective, we're going to give it a priority of 1, saying that we want to solve it first, and or before lower priorities. And we're going to give it a name. And then we're going to set our cost objective be the sum of all the costs, and we're going to say it's a lower priority than objective 0. And then we're going to make a call to optimize. So this is a very clean way of defining multiple objectives. If you wanted to implement that yourself, you'd be reading out a solution, changing the model, and then solving the model again. So lastly, we're going to do some status checks. We're going to check for, infeasible, unbounded, those types of things. This particular model should never be any of those, just due to the way we formulated the model. If we hadn't made those soft constraints, it would be infeasible almost all the time. And then we print so line 89 through 92, that's just processing the solution. At this point, you could easily write that back to a database. You could write it to the next model, whatever you wanted. And then lastly, we're going to do some cleanup. So here in under 100 lines of code, we have implemented this model. And, it's important to note that, this same model written in C or some other things, I've written it before, and it ends up being thousands of lines of code by the time you actually check a lot of memory safety and other things. And so the fact that it's so, compact makes it easy to debug, easy to read, easy to change. So this API, I can't stress enough how much I love working in this API. Okay, so another important topic that I would address is variable hints. So like I said, we use publicly available regulatory data. That data is constantly changing. The states and the federal government, they have different frequencies. Some of them update monthly, some of them update annually, some of them update monthly, but they're on the 15th of the month or the 1st of the month. And so we're always getting new kind of facts or volumes or information. There's wells always being added, systems being added. And depending on the region of country, so how big the model is, some of these models can take seconds, some of them take over 24 hours to run if there's a large number of wells and systems and it's complex. And so if we need to run this model a large number of times and every run of the model takes, we'll call it 24 hours, that could present a problem. But one thing to note, typically when the data changes, it's just adding a little bit of data, tweaking a few things. It's not going to make catastrophic changes to the solution. Every time we run the model, we don't get a completely new reallocation of wells to systems. It's a few hundred wells here or there that shift based on our new fact. So is there any way that we could feed our existing solution back into the new problem to help make it run better? Yes, that's variable hints. So variable hints can help the algorithm make good decisions based on outside knowledge. It can, suggest this as a possible starting solution, or as it's progressing, it can help try and determine bounds and different things like that. And it drastically reduces the time required to update models with new data. With multiple objectives, there's a pretty straightforward path to implementing yourself. It's just extra work. This is something that's a little bit more difficult if you want to implement yourself with just an open source solver that doesn't support variable hints, because for a couple reasons, you're going to have to go back in and probably actually change the way that branching is done. You're going to have to change the way the initial solutions are found, some of the heuristics, different things like that. And so this is one of those features that is a lifesaver for us. All of a sudden the model runs, instead of being 24 hours, now all of a sudden it might only take an hour to rerun a model. I've used this quite a bit. I've never experienced a large increase in time. So Gurobi's pretty smart. If a variable hint's wrong and they're like, it's not correct anymore, I haven't seen it waste a ton of time in execution, but I've definitely seen it help a lot. So this is a feature that can definitely help when you've got a production model that you're running over and over and over. You can feed existing solutions in to speed up some of the execution time. So a few closing thoughts. Like I said towards the beginning, mixed integer programming is an excellent framework for stating a problem. And it's not just for decision making. I know that integer programming has and will continue to be very useful for planning, scheduling, routing, partitioning, all the classic problems that you think of with optimization. But there's a large number of problems that you might not even think of using linear and integer programming for, that it absolutely can be very helpful for solving a problem. But even if not solving a problem, just stating a problem. One of the things that I have found is just the modeling process is very helpful to understanding the problem. To actually sit down with the business owners and understand, well, what are the things we can change? What are our actual constraints? If we have soft constraints, well, what's the importance of those soft constraints? So even if you don't end up solving the problem, just modeling the problem within the integer programming framework can be very helpful to understanding it. Another thing I'd like to point out is that advances in hardware and software have greatly expanded the scope of what is possible. So, I'm not going to give the exact numbers just because, I don't run the benchmarks, but I think, just since Gurobi, version 1 to what they're at now, I think version 8.1, I think it's over 50x that they've sped up on the average problem set that they're looking at. And that's just the history of Gurobi. If you go back and look, maybe speed up from the 80s to today, it's multiple thousand-fold due to different hardware and software advances. So maybe there was a problem that got formulated 20 years ago that wasn't solvable. Well, it might be solvable today, or we can solve it thousands of times faster. For East Daley, integer programming has been very helpful for our GMP allocation models. My very favorite thing to say in the office is that you can't prove the model wrong without making it better. So if you come to me and you say, hey, I know this well doesn't belong to this system because of X, I can make that a constraint and I can put it back in the model. If you come to me and say it doesn't line up because it doesn't meet this volume, well, guess what? We can put that as a constraint and we can give it a stronger penalty. And every time you can prove the model wrong, if you think the model's wrong, I can't really do anything about it. But if you can prove it wrong, I can put that into the model and make it better. Like I said, it's, linear constraints is a very simple framework for adding new categories of facts. So, we talked about geography, we talked about volumes, but let's just say all of a sudden a new data set becomes available where people have to report how many wells are behind each system. Well, that's really easy. We could just, sum up all the different allocation variables that are binary and make them equal to the count on each system. So, when new types of facts come out, there's a very straightforward way of adding those to the model. It's balanced. So before we had this model, people would look at systems one at a time. So they'd come in, they'd look at a system, they'd draw a circle on the map, they'd take, okay, I want all these wells. Well, inevitably, when you circled one system and then circled another system, those circles might overlap a little bit. So you'd double count some wells, you'd miss some wells. And so it was, frankly, wasn't very perfect analysis. So by solving everything simultaneously, yes, there will be a few wells that are allocated incorrectly, but it's balanced across all the different systems in the area. And then the last kind of thing that's second to last thing that's very useful is gap and bounds. So, we just as easily could have come in and written just an algorithm or a heuristic to partition the wells between the systems. The problem with, heuristics and algorithms is you really don't have a sense of how close to being optimal they are. So one of the features I really like about optimization is because of some of the mathematical qualities of what they've proven with the linear programming, we can find a bound. We can look at what our current incumbent solution is. We can calculate a gap, and so I know that, hey, nobody's algorithm with the same exact weighting and data can do better, more than say 2% better than this. It's been so useful to us, we've applied for a patent. So the application of this model to solving our natural gas supply chain, we've applied for a patent on it. And then I'd like to close by saying that there's a lot of Gurobi features in their API that speed up development time and accuracy. The Python API itself, the multiple objectives, variable hints, and there's many others depending on what type of problem you're working on that have really made my life easier over the last several years. So that's everything I have prepared. Does anyone have any questions? You can submit them in the GoToWebinar tool, and I'll be happy to try and answer them as best as I can.
Thanks a lot, Levi. Yeah, so now it's time for questions. Yeah, I personally enjoyed it a lot. So I followed the presentation. It was first like, okay, so this is an assignment problem. Ooh, now you have knapsack constraints. Ooh, now you introduce soft constraints. Oh, now multiple objective. Oh, and yeah, then someone comes around the corner with some facts, and you have even more constraints. So wow, a great example on how a MIP model can add value to this problem as a part of a bigger solution. Very, very nice. So let's in. Questions are coming in. Well, first question is, what is the typical problem size?
So the typical problem size, I'll give you the range. So our biggest problem has, let's see, it's 400,000 wells and 200 processing systems. So basically, I'll let you do the math. 400,000 times 200 binary variables, and then we generally solve over like a 4-year time period. So you've got 48 times 200 continuous variables, and then several 100,000 constraints. That's kind of our biggest problem. We have some areas of the country that may only have a few thousand wells and 20 systems, and those are a lot smaller. The big ones take 24 plus hours to solve. The little ones take seconds to minutes. It is also important to note that, like, with the big formulation, there's a lot of optimization that could be done within that. So, of the 400,000 wells, even within that 400,000, there's some pretty clear, like, this well will never go to this system. So we could put a lot of that in. Quite frankly, I don't even have to. The pre-solver for Gurobi works wonders, and it generally eliminates a few 100,000, if not million variables pretty quickly, that I don't have to worry about trying to optimize all my code. So.
Very cool. Another question regarding the model is, so you mentioned those facts. So someone tells you whatever, that well cannot be assigned to a certain system. Can you give an example of what type of facts there could be and how that would look like as an additional constraint?
Yep. So let's just say that, and because we have a team of analysts that they're industry experts. They're looking at this information on a daily basis. So let's say that there is a regulatory problem in a specific county in Oklahoma. The state may come out and say, hey, we're having issues. We need you to fill out this form and file additional data that's not typically required. And when digging through those forms, you might find that a processing plant has to actually list who the producers are or who the companies are that feed them data. Now, all of a sudden, we can add constraints that say, hey, this system can only be made up from wells that are operated by these 10 companies. And so we can add a fact. Or you might get, we'll find some information that says, hey, this is a high pressure gathering system, so it can only handle high pressure wells. And so we can go say, well, then it shouldn't get any low pressure wells being added to the system.
Interesting. So facts mean you probably, in this case, you probably remove variables, right? Because previously you were allowed to assign something, but now you're not anymore. So,
yes.
So cool. So it doesn't necessarily have to be additional constraints, but it could also be to reduce the complexity because you have more information about what's possible and what's not.
Yes, although a lot of the time I just go ahead and implement them as a constraint and let the pre-solver get rid of the variables.
Yeah, I think that also works well as a general recommendation, of course. Maybe let's look at a few questions about performance. So, of course, you mentioned those large models. So maybe can you tell a little bit the performance story? Something about, okay, how did you start? And maybe you noticed, oh, that takes a lot of time. You mentioned variable hints to speed up the process. So maybe you can share a few interesting maybe experiences during the development that helps you to get to the performance that you need for the application.
Yep. So initially, when I was prototyping, I would use smaller subsets of data just so they'd solve in a reasonable amount of time. When we blew it out to the full, largest model we have, it was, running for a long time. But going back to the idea of having a gap percentage, that's very helpful because, I can immediately see that, okay, even though it's only been running for 2 hours, I'm within 5% of the best it could be. And so that gave me kind of a sense of confidence that, hey, even if this doesn't improve the solution at all, we have a reasonable solution we can work with. And so then, we went ahead, this is development, so I let it run for a few days. It did solve. Then I tested, changing some of the data, feeding back in variable hints, and because it then ran in a few hours, that was the extent of our performance testing.
Okay, did you work with a support team at Gurobi?
I did not work with the support team as far as actually improving the performance or the model runs, but just getting an initial trial license to run it, we did that. So
that wasn't actually a user question. That was just my question as a member of that of that team. I was just curious. Okay, let's see. So, oh, you mentioned MIP gap, which is interesting because, of course, it allows you to get a sense of how good you already are, or how good how much better you can actually get if you spend more time. Maybe from the other side of that medal, could you give an indication of, and that's how I read a question that came in, what's the value add here? I mean, what you do is you use a MIP model to, like you mentioned, you fill the gaps. So it's a little bit like regression or something. So you basically construct a system that has the property that it fits to what you have. So you get, and you get something that gives you more details on something where you actually don't have details. And so having these details has probably a few very interesting implications for the things that come after solving the models. Maybe you could share a few details about that.
Yes. So going back to that, that diagram of the supply chain. Now that I know the individual wells behind every single processing system, and I say no because it's a model. That doesn't mean it's correct, but with all the information we have, it seems reasonable. So I know the wells, so I can use statistics to forecast the volumes for each individual well. So now I can forecast what the throughput is going to be of that specific processing system at a pretty granular level. Now that I know the forecast through that processing system, I can look at historical performance of that plant and know that how many gallons of NGLs are produced per MCF of gas, and now I can forecast the NGLs that come out. I know which NGL pipes connect to which processing plant, so now I know how many NGL volumes are going to be feeding into each NGL pipeline. We know which NGL pipelines feed which fractionators, and you can just keep propagating throughout the chain. If you didn't know which wells were feeding which processing plants, you can't forecast the plants very accurately. So knowing the facts or filling those gaps really just allows us to improve accuracy as we propagate questions throughout this supply chain of, once again, if I know the individual wells feeding a processing plant, if this processing system, back to my question about what if Chesapeake is going to declare bankruptcy? Okay, if I know that this processing system is made up of 10% Chesapeake wells, I can quantify the risk behind that processing plant. I can quantify the risk behind the NGL pipelines attached to that plant, and I can keep propagating that question throughout the value chain.
Cool. Is this something that runs fully automated, or is it still a manual process? So every day or every whatever.
It is fully automated with the exception of when people have new facts. That process, if we have to actually add or change some constraints, that process we have to go in and tweak some things. If they're just merely changing the data, that's still automated. But if they actually want to come up with a new class of constraints, or we actually want to change the objective hierarchy or different things like that, then we have to manually go in and tweak some things. But yeah, it's automated in the sense that it just runs when we get new data. So.
Cool. Have you, another question is, have you looked into, for example, decomposing the problem? Is this something that, for example, spatial, that you say, okay, we do one model for north and one model for south? Is that something that would make sense here, or is it like the overall system? Is that something that is that needs to be considered? So would you would lose probably something when you do that?
Yep. So we have kind of a high level done that. So like I said, the Northeast I solve different than I solve Texas, than I solve North Dakota. Within a basin, we could look at doing that more. But like I said, at this point, it kind of meets our business objective. It runs in a reasonable amount of time. And so we haven't looked at, even to Kostya's question about, eliminating variables as opposed to just adding constraints. We could do that if performance was a real issue and we really needed it to get it closer to real time. We could do a lot of things like that. Honestly, the solver's been good enough at this point that we just kind of, hide our, shut the bedroom door and hide how dirty it is, and it's good enough.
That's great to hear, especially from the support perspective, because usually, you know, performance is never enough. Yeah, and when it's enough, there is a new aspect that you can put into the model to make it even more complex. That's usually a never-ending story. Let's see. So here's another question. So in order to speed up runs, so you mentioned variable hints. Have you looked at, for example, variable hint versus MIP starts? So giving hints versus, you know, providing partial or even previous solutions to start with?
So the issue with MIP starts is you're giving it kind of a more concrete starting point, and the data has changed. So maybe there's 10 new wells that have been added. Well, those weren't in the previous run of the model. So I'd have to do some work to try and, you know, assign them somewhere, figure out how to, you know, get the MIP start to look exactly like I wanted it to, versus the variable hints. I kind of let you guys handle the trade-offs of when to look at a hint versus when to not.
Okay. Then something that is usually a dangerous question when you talk about a MIP solver, you mentioned nonlinearities. I mean, we're talking about, you know, networks of oil and gas. So is there something in there that you had to simplify, or something that is, you know, nonlinear in a way that you maybe couldn't add it to the model?
Yeah.
Or...
So you know, this model, just for simplicity, what I demonstrated today, we looked at absolute fit error. What we really wanted to look at was squared error. So actually, for each, you know, fit variable, we actually have a series of piecewise constraints that branch out. So we actually approximate squared error. You know, we look at, you know, error within 0.5%, then error within 1%, then error within 2%, error within 4%, error within 8%. And so we kind of approximate, you know, squared error as opposed to just absolute error, because what we don't want is one system to be wildly off while all the systems are, you know, spot on.
Sure. And the reason why, you know, so have you tried modeling it explicitly? So just putting the squares into the model?
Yeah, I haven't tried pulling the squares in the model at all. I know there's been some recent work in, you know, quadratic objectives and quadratic constraints. I haven't looked into any of that yet. So.
Yeah, we're actively working on that actually, because the current Gurobi version is limited to the convex quadratic stuff, and that is going to change with the next release. So maybe I mean, if you say it works well for you the way it is, then maybe that's something for the next project. But of course, quadratic error is something that you see quite often, especially when it comes to risk.
Yeah. And personally, I might look into it just for fun, but from a business perspective, I probably can't get them to say, hey, here, go spend another 2 weeks looking at this, because it works.
Yeah. Let me see. One more thing. So if you have two runs, and you mentioned the data has changed, but only a bit. Do you consider previous solutions? So is there any value in whatever, having something in the objective function that makes sure that the solution doesn't change too much compared to the previous run? Is that something that would make sense, or is that not relevant?
It would, and that's a question we're kind of actively actually looking at right now. Is, you know, once again, nobody actually knows the solution to this problem. So going back to my statement of you can't prove the model wrong without making it better, that's correct. But at the same time, you really don't have any way of validating your data other than saying, well, it meets everything we know. But we're actively looking at, you know, internally, what kind of controls can we put on all of our different things to say that, hey, we had a change of greater than this amount. What does that mean? Does that mean that we were wrong before and we're right now? Does it mean we were right before and wrong now? Does it mean we were wrong both times? So it's something we're actively looking at, but it's not a problem we've necessarily solved to date.
Sure. So feasible solutions, or actually finding the first feasible solution. Like I think you mentioned that you relaxed one constraint a little bit from an equality to an inequality. That was, I think, the assignment from wells to systems, where you said, okay, it's less than or equal to 1 instead of equals 1, which is sometimes you want. So that probably allows you to start with solutions that actually violate that. But hopefully at the end you will have solutions where this is not violated. Or is that something that is helping the overall process? So relaxing it first, but then waiting for a solution that actually doesn't violate this?
Yeah. So once again, the data is imperfect, and so what we end up having in, I'm going to say, out of the maybe 16 models we run, there may be one that this isn't an issue, is the data doesn't line up to the degree that there's generally at least maybe a few thousand cubic feet of gas that we either can't associate to a system, or it just doesn't line up. And it's entirely possible that somewhere underground there's a leak in a pipe, and so the well is producing it and the processing plant isn't seeing it. And so any well that doesn't get assigned to a system goes into a balancing system, and we just do that with post-processing. So any well I come across that doesn't have a system just gets assigned to a balance system, and then we obviously monitor those balance system closely, that, hey, if all of a sudden the balance system has hundreds of thousands of cubic feet of throughput, all of a sudden we now have an issue where likely what happened is a new processing system's been added that we weren't aware of.
All right, Levi, thank you so much. That was really, really, really interesting.